The proposed method is designed to acoustically characterize the control room. My acoustic characterization here comes from an evaluation of the physical and acoustic parameters found in the technical literature. The results were then compared with the technical recommendations. For measurements regarding energy variation in time, impulse response technique was applied. To capture the frequency response of the control room, pink noise was emitted from the audio monitors. Our review is very simple, so very simple equipment, so everyone can easily reproduce at home or in your home studio or whatever you work. For measuring impulse response, the audio signal was captured by a Behringer ECM, the ACM 8000. It's a really cheap microphone, an omnidirectional microphone, and converted to a digital using the just the M audio fast track interface. That's pretty simple, pretty easy. Everyone can reproduce at home. The software used for this measurement was the Dirac from Brew and Care, installed on the portable computer. The acoustic parameters obtained by means of the software were reverberation time, energy time curve, the waterfall graph, and the Schroeder's plot. Here we can see, I'll show, okay, next picture, a simplified block diagram depicting the connection scheme of the necessary equipment to measure the acoustic parameters which were obtained using the impulse response of the control room. It was something simple. Here's our speaker, okay? As I said, the omnidirectional microphone. Here the interface is our M audio interface. And can be both in this case, all right? The Dirac for impulse response and the Smart. They're both in a laptop. Sound signal employed to obtain impulse response of the room was 4 repetitions of an E-sweep. You can choose different pulse, okay? In this case, we choose 4 repetitions, and it was direct and E-sweep with the duration of 5.46 seconds. For measuring frequency response, the same microphone was connected to a fast track interface. The software used, as I said before, was the Rational Acoustic Smart. The version was 7.2.1. The microphone used to capture audio from the monitors had its capsule pointed towards the speakers. A shot mount was adapted to meet this need. So I'll show here. There's a microphone and a shot mount. And let me show how it was working. So since we were measuring 5 channels, 5 monitors, I adapt this shock mount here to keep the microphone in the same position, right? So no matter how much I rotate the microphone, the position is still the same. To measure the background noise in the control room, a sound pressure level meter model 2238 from Brew and Care was used. The measurements were made between 31.5 hertz and 8 kilohertz in 1 octave bands. The background noise spectrum was measured from 3 positions. The first was measured at the reference listen position, right here where I am, where the engineer works. And the other 2 positions were 1.5 meter away, left and right. These positions were prioritized because they are in the most useful area in the studio, where normally the audio engineers produce and the artists work, our sweet spot. The spectrum of the background noise was calculated based on the arithmetic means of the values obtained at these 3 points. Another measurement of background noise was made with the computer located in the machine room. So we're gonna compare the results. The monitor used were the Mackie HR824, right? 824. According to the manufacturer's specification, this monitor can reproduce the frequency between 39 Hz and 20 kilohertz with a maximum variation of plus or minus 1.5 decibels. No equalization or filtering was applied to the audio monitors. The control room is approximately 30.6 square meters or 330 square feet, around 330 square feet in area, with an approximate volume of 104 cubic meter or 3,600 cubic feet. The studio has large amount of absorption in the very front, in the front area. The back of the room is also acoustically treated with a great deal of absorption, with exception of the QRD. We can see a QRD coaxial diffuser installed to prevent specular reflections, and a small glass window just above the diffuser, which provides natural light to the environment. It's something that I really like in control rooms. If you can, if you design your own room or to somebody else, natural lights helps a lot. Makes you feel more even cozy, even comfortable. That's a good, if you have this alternative, you should definitely have a natural light. So as we can see here, here's a picture, a plan of the control room. We have, as I said, here some traps, some bass traps in the corners, all right? We can see the diffuser, we can see our reference listen position, and the speakers too. The acoustic room analyzed was acoustically assessed in the reference listen position, which is equidistant in relation to the audio monitor. Acoustic parameters were measured on axis with the microphone capsule pointed at the speakers in order to verify that the results meet the recommendations adopted for this type of configuration. To measure the frequency response, a pink noise signal was sent to the speaker with the sound pressure level equal to 78 decibels SPL, as recommended by EBU. To measure parameters in function of time, we use the impulse response technique. In this case, we use an E-sweep as a sound source. We use for reverberation time, energy time curve, the Schroeder's plot, and the waterfall graph. I'm measuring each monitor, in this case here, separately. But when you have a subwoofer in a control room, you can have different measurements with the subwoofer in different positions. You can use like we can use some small reels like this one. I have one here. You can have your subwoofer and move with the wheels. That shows in real time an interaction between the sub, the room, and the stereo monitors.